So we start off here very simply. This is the beginning of our general chemistry course, the first semester of the two-semester sequence. And we probably want to start off as simply as possible. So, what is chemistry? Why are we taking this course? What are we going to learn here? And so a basic definition of chemistry, and it's one of those definitions that sounds very simple when we say it, but there ends up being so much to this that we can spend our entire lives studying this field. So chemistry is a field that is the study of the composition, so in other words, the composition, what things are made of, the properties, and how we transform matter. As we said, these are three different areas that we can get into, and these encompass a large variety of different things. Now, when it comes to chemistry, we break chemistry down into a number of different fields. And while some people might make this number higher, typically I like to say there's about 6 basic fields, 6 disciplines within chemistry. And we start with my favorite, which is organic chemistry. Organic chemistry focuses on the study of carbon-based compounds. This becomes relevant and important because all living species that we know of are carbon-based. And our entire drug industry, pretty much any pharmaceutical compound you might be familiar with is very likely a carbon-based compound. Organic chemistry gets into things like polymers, food and nutrition. All of this is carbon-based, all based on organic chemistry. Very closely related to organic chemistry in many ways is biochemistry. Biochemistry is when we specifically, not only are we looking at carbon-based compounds, but we're looking at biological chemistry. Chemistry that takes place in our bodies or any biological system. In organic chemistry, this is in many ways the opposite, not organic chemistry. So organic is carbon-based. Inorganic really studies a lot of metal-based compounds. Uh, and then we have 3 more we'll mention: analytical, physical, and environmental. And we don't want to say the chemistry is limited to just these 6 areas. As I said, some people might define more than 6 areas. Some areas are just parts of these areas. But these are sort of the 6 very broad categories. Physical chemistry looks at the application of physics to chemistry. It often deals with a lot of computational work. Environmental, hopefully, is pretty obvious from the name, but we're looking at what chemistry, how it affects nature. This can be soil chemistry, it could be looking at aquatic environments, it can be atmospheric chemistry. And finally, analytical. Analytical stresses the separation, identification, and quantification of chemical compounds. And if you've ever learned anything about forensic chemistry, a lot of that's covered in this analytical field. But I want to go back to our original definition, because in our original definition, we mentioned three things: composition, properties, and transformation. So what do we mean by those three things? So composition, what is it made of? So whatever matter we're studying, we're literally trying to determine what is it made of. Is it more than one compound? Is it a single compound? Is it a single element? Can we identify those compounds? Can we identify the elements that make those compounds up? If it's a mixture of different compounds or different elements, what's the percentage of them? And we not only need to know, what the elements or compounds are, but we need to know quantity. If we have a compound that's made up of hydrogen and oxygen, that tells us something about the compound, but it doesn't tell us exactly what it is. Being made up of hydrogen and oxygen, it could have two hydrogens and a single oxygen. We probably all recognize that. As water. But if we add in a second oxygen, what happens to it? Now it's not water. Instead of water, we now have we have something you might find in your medicine cabinet: hydrogen peroxide. So it's not enough just to know what elements are involved. We have to know how many of them. All right, what about properties? Well, we can put properties into four different categories. We have our first group of two categories, which look at physical and chemical properties. And then we have things like intensive and extensive properties. So what are these categories? Well, physical properties, we're talking about things that deal with, you know, in some cases it could be the appearance, what's the color or the shape of something. It could also be something like the melting point, the temperature at which that substance melts. The way we identify a physical versus a chemical property is that in a physical property, measuring that property doesn't change what the compound is. So if you take ice and you melt it, it's taken on a different form, but it's still water. Solid water versus liquid, but it's still water. So that would be defined, as a physical property. A chemical property could be something like burning, combustion, rusting would be a chemical property. Acid-base reactions, corrosion. In a chemical property, these are how chemicals react. And observing a chemical property actually changes what the compound is. So again, a physical change, it alters the appearance of the compound, but not what the compound is. A chemical change actually changes the structure. We also have these properties, we can define intensive and extensive property. An intensive property does not depend on how much material we have present. Whereas an extensive property is dependent on quantity. So what would be some examples? So an extensive property, again, it's dependent on the quantity. So the mass of a sample would be an extensive property. As would something like its volume. Those are both dependent on how much you have. On the other hand, an intensive property does not depend on the quantity. This could be a compound's melting point, its boiling point, what color it is. Something that does not depend on how much we have. Our third category, our third thing that we mentioned within the definition of what chemistry is the idea of transformation. So transformation is how we're going to change matter. And that transformation can be physical. So physical change, again, is going to change the appearance, but not what the substance is. So an example of that could be something like water as a solid, or we refer to that as ice. If we melt that, now we get liquid water. Have we changed the appearance of the water? Yes, it's gone from a solid and now it's a liquid. Have we changed what the water is? No, it's still water. It's still an oxygen with two hydrogens. In a chemical transformation, we're actually going to change what the substance is. So an example we might be familiar with, if we have iron, and don't worry about what these numbers out in front mean if you haven't seen them before. Later on in the course, we'll learn that these numbers have to do with keeping the equation balanced so that we have the same number of atoms on each side of the equation. But iron and oxygen can react, and we get iron oxide or rust. That's an example of a chemical change because our substances, both of them, both the iron as well as the oxygen, are no longer what they originally were. So finally, before we move on from this section, a couple definitions we want to be familiar with. So we've used this term a couple times already, matter. So it'd probably be good if we now stop for a moment and define what matter actually is. So matter is anything that occupies space and has mass. So very broad definition, but that's how we define matter itself. Now we want to be careful with a couple of these terms here because in many cases we often hear that mass used interchangeably with another term. And so we want to stop for a minute and make sure we understand what those two terms are. And those are mass and weight. And oftentimes when we're talking about weight, that's a term we use on a daily basis. What the term we really should mean is mass. And these two are not equivalent terms. So what are they? Mass is the amount of matter. In whatever object we're looking at. Now weight is related to mass, and these two terms are related. But what's the difference? Weight has another influence on it. Weight is how much an object is attracted by gravity. So again, we just want to be careful that with the term that we're using, and pretty much from now on in this class, mass is the one that we are looking at. We almost never talk about weight. All right, what are the other definitions we want to make sure we are just familiar with before we move on? So we're going to talk about element. What is an element? Versus, we'll talk about what a compound is. And then we'll look at mixtures. So an element is the simplest type of substance that has unique properties. A compound is when we chemically combine two or more atoms. And there's no upper limit on this. Elements are what we find on the periodic table. Things like hydrogen, oxygen, nitrogen, carbon, gold, silver, so on. As soon as we combine two atoms together, so oxygen gas, what we breathe in is actually O2, so that means it's a compound. Same thing with H2O, water, C6H12O6. Now we've got 24 atoms put together. That's our formula for glucose. And there's really no upper limit on the number of atoms. For those of you who are interested in biology, you'll learn eventually about proteins. Proteins can contain thousands or more atoms put together. All right, our final definition here are mixtures. These are two or more, and that two or more is either compounds or elements mixed together. But when we say mixed together, we don't mean that anything chemical is going to happen. We just mean that they're brought into contact with each other and they mix. And mixtures that we make up can be both, they can fall under the heading of homogeneous. If they're homogeneous, those are mixtures that are uniform throughout. Or heterogeneous. When they're heterogeneous, they're non-uniform, and you can typically see phases. You can often see this if you're looking at a bottle of Italian salad dressing. You can see the oil layer and the water layer. Um, if you're eating a bowl of cereal with milk, that's a mixture. You can see the milk and you can see the cereal separately. They don't combine to form a solution that's uniform. On the other hand, what would be an example of a uniform solution? Well, one example is the air around you. You're surrounded by it. It's a mixture of nitrogen and oxygen and carbon dioxide, water vapor, many other different gases. But you don't see those separately. It looks uniform. Vinegar, again, it's a mixture of multiple compounds, but you only see a clear solution. So as we move on in this course, a lot of different things we're going to learn about compounds. But one last thing I want to say about mixtures before we end this part is how important some of these things can be and how important an understanding of science and chemistry can be. So here's a listing of ingredients. So if we go back to what we were on the previous page talking about mixtures, this would definitely be a mixture. Now, what do you think? Is this something that you'd want to um, consume? Would you want to eat this? A lot of, very chemical sounding names in it. Turns out, when you see what it really is, one of the interesting things we learn in chemistry is when we have these very complicated sounding names, they're not really so bad. And so you can see here this pineapple, which I don't think is the same ingredient list I had up before it, but has, quite a few things that sound like chemical names. But you don't see those when you go buy a pineapple at the grocery store because they say things like this don't need ingredient lists. But these are a set of posters that was made by a chemist who said, what if we had to put ingredient lists on so-called natural foods? There's the list of what is contained in an egg. Or a coffee bean. So that's our introduction for the course, and next thing is we'll move into the scientific method.